The title of this class may remind you of outer space, and of course it's not. We're going to still stay here on Earth. However, some of the concepts involved in it may look like they're coming from outer space and they belong to some different civilization or something like this, mostly because you are not used to them. We're taking another step towards what we call abstract algebra. In fact, it's going to be probably the biggest step towards abstract algebra that you have seen so far, and so it's going to look very uncomfortable at the beginning. But remember, there is always that stage of confusion and feeling uncomfortable whenever you're learning something new. So don't be frustrated by it, just play with it and just keep in mind some of the things that I'm going to tell you. Also, at the beginning of the first little while of this class, it's going to be some general considerations, not much mathematics, but don't think of skipping them, because they're going to be considerations which are going to help you tremendously in what we're going to be doing later. If you miss the point of what we're about to do, then you're going to find a lot of difficulties with it later on. But if you get the main point of what we're trying to do and some of the main difficulties, then probably you're going to be better able to address those difficulties and overcome them easily. Alright, so what are we going to do here? The idea is the following. Let's compare vectors and matrices in what we've done so far. Okay, there are some features of vectors that are unique to them. Okay, such as dot products. You cannot do the dot product of two matrices unless you see them as vectors. But they're not. The dot product is not really something that belongs to matrices. It belongs to vectors. On the other hand, there are some features that are unique to matrices and not to vectors, such as determinants. We can't even talk about the determinant of a vector unless we rewrite that vector entirely as a matrix. But again, we're back into dealing with matrices. So some of these features are specific to one or the other. However, there are some features that are in fact common to both of them. And in fact, I've been insisting on the fact that vectors and matrices are really two ways of looking at the same kind of thing. Matrices have additional structures, but they're vectors, and vectors can be thought of as matrices. So what is common between these two types of objects? Both can be added, both can be multiplied by a scalar, and both have an opposite, right? If I have a vector, I can construct its opposite vector. If I have a matrix, I can construct its opposite matrix, and so on and so on. Also, both have a special element which we call the zero element, so the zero vector or the zero matrix, and both have some kind of unit elements of some sort. Vectors have unit vectors, matrices we have the identity matrix that acts as a unit in some way, and so on. So what we're going to be doing is we're going to try and find a common core between vectors and matrices. We're looking for what is it that is really common to both of them and it makes them similar in such a way that we can transfer information from one set of objects, from vectors to matrices. Okay. So also, the other important thing that we're going to be noticing is the fact that there are other sets of objects that also have the same properties that we have seen already common to vectors and matrices. For instance, if you think of polynomials, okay, they also can be added, they also can be multiplied by a scalar, they also have a special zero element, they also can have an opposite, and so on and so on. And if you think about it, the set of continuous functions has the same properties. And the set of solutions to certain differential equations, well, you may not be able to see that right away. You may not have enough experience with differential equations to figure that out. But in fact, there are certain differential equations whose sets of solution have the same properties. They can be added, multiplied by a scalar, they have a zero element, and so on and so on. Okay? So what we're trying to do is we're trying to figure out what is essential, what is to the core. Okay? Which of these properties are really, really important? And also, can we generalize these properties to other spaces? And why would we want to do that? Is there some advantage to generalizing some of these properties and trying to figure out when they apply? So let's have a look at this question of why do we want to generalize? Why do we want to find out what are these common core features, properties, and why do we want to generalize them? Well, the idea is that we want to identify these common properties and so that we can extend old knowledge to new sets. If we find out that there is something useful, interesting in a what we're going to call a vector space of one type, and we realize that that property really depends only on the basic vector space properties, then we can generalize that to any other set that has those properties. Now, you may find it hard to parse what I've just said, but the idea is if we can find something in common to one group, one set of things, and we realize that another set, a different set, has similar basic core properties, then we can also extend to this new set the extended properties. Probably that will become a lot clearer as we go through some examples. The other thing is also what we can do is we can develop tools that can be used on all objects that have a similar thing. For instance, I said that the dot product is something which is specific to vectors and does not extend to matrices. What we may want to do is ask ourselves, okay, is there something about the dot product that we may be able to extend to other things like matrices, polynomials, functions, and so on? And in fact, we're going to be able to do that at some point. We're going to analyze what is the essential feature of the dot product, which is actually generalizable, and we're going to use that information and therefore somehow extend the dot product to other kinds of sets. Also, we may want to do that to identify certain properties which are, on the other hand, specific to certain objects. There may be some things which are simply not generalizable. Doesn't matter how we twist and turn them, they do not depend on the basic core properties, but they depend on something which is specific to a given set. And so we realize that those properties make that set unique, and that's also important to know. Also, certain operations, some things that we can do in certain contexts but not in others. So again, what we're trying to do is figure out, okay, what is generalizable, what is common, what is core, and what is specific to a certain set.